Okay, thank you very much. Good day, and thank you for presenting me the microstructure of dynamic recrystallization after in titanium 6-4 after yeah, complex multi-axial fatigue stress test. It doesn't work. Yes, yeah. In this presentation, we will focus on the dynamic recrystallization in titanium. Sorry, but it doesn't. So I need to stay here. Try. Okay, all right. Okay, thank you. Okay, thank you very much, and good afternoon, and thank you letting me presenting the microstructure of dynamic recrystallization in titanium after some complex multi-axial stress fatigue test. In this presentation, we focus on systematic investigation of dynamic recrystallization and its effects of texture, orientation, and grain refinement in titanium 6-4. To get a better understanding what dynamic recrystallization is, I will first show you some results of the from the literature of the microstructure of titanium 6-4 after dynamic recrystallization and grain refinement. Okay, here should be a picture of TEM investigations where we can see in titanium 6-4 after dynamic recrystallization and after laser shock peening, how the microstructure is developing, but actually, we can't see any pictures. Okay, thank you very much. After some trouble, finally I can show you the pictures. Here we can see TM characterization of the microstructure of titanium 6-4 after laser shock peening. With this surface strengthening method, ultra high plastic strain has been applied. And in the microstructure, the results of the microstructure show the accumulation of dislocation and contributed to formation of dislocation tangles and dislocation walls. This high density dislocation walls and tangles transform into subgrain boundaries after annihilate and rearrange themselves, and these subgrains transform into high angle grain boundaries. This shear bands induced dynamic recrystallization mechanism plays a role in texture, orientation, and grain refinement. So why titanium 6-4? Titanium 6-4 is the most common material used of titanium alloys with 6 weight percentage of aluminium and 4 weight percentage vanadium. Here vanadium stabilizes the cubic beta phase, while aluminium stabilizes the hexagonal alpha phase. And the test material itself, the cubic beta phase, is represented by only 5%. The alloy is characterized by its biocompatibility, good wear and corrosion properties, as well as sufficient fatigue strength, and is therefore good for implants and aero engine as engineering components. However, under complex working conditions such as high temperature and stresses, titanium components frequently deformed and even fractured, and this affects the reliability of the alloy components. Exactly, and these mechanisms under these complex circumstances needed to understand very well. To understand the mechanisms under combined pressure torsional fatigue circumstances, tests were carried on specimens with specific sample geometry and under extreme stress parameters. Here we can see a schema to illustrate the torsional movement during the tests. During a constant pressure, the torsional movement have a reversal point of cyclic torsional movement, or the torsion has a reversal point of cyclic torsional movement, and this is recorded during the test about the cycles. The output of the shear stress is in negative as well as in positive range, while the negative shear stress is the time change cyclic torsional movement, first in one direction and later in the opposite direction back. Okay. As I mentioned, the tests were carried out on cylindric double cone specimens with a 10 millimeter diameter and a hexagonal section to clamping the specimens into the testing device. The tests were carried out on the testing device Bionics 858. The testing parameters for the test series included constant pressure by 400 megapascal, by different torsional angles, and by a frequency of 2 Hertz. In that video, you can see a simplified model how the multi-axial load was applied. As I mentioned, the tests were carried out with different torsional angles. In this study, we focus on the samples with high torsional angle because to get a better understanding of the plastic deformation. If you look at the mechanical behavior, we first recognize that the yellow and orange shear stress curves belongs to the sample with a torsional angle of 14 degree, and that the gray and blue shear stress curves belongs to the sample with a torsional angle of 15 degree. If you look at the results of the mechanical behavior of the highest torsional of the sample with the highest torsional angle, we recognize first that the specimen compress actually more than 10%, and that the shear stress shows in the very first cycles a material softening, following by a constant shear stress until 1,000 cycles, and then the shear stress increase a little bit, and the shear stress drop occurs at 1,400 cycles, accompanied by crack initiation. Here to mention that the actual compression, the highest value of actual compression is by 11.47%. When we compare it with the sample with 14 degree torsional angle, we see some similarities. The shear stress curve decrease constantly until a more pronounced shear stress drop can be seen at 1,900 cycles, accompanied here again with a crack initiation. Here the actual compression is under 10%. So we can see plastic strain takes place both cyclic accumulated and axial compressed. Yeah. To get an understanding of the stress distribution, the stress distribution was simulated for the very initial cycles. Here we can see, or the simulation provides us a clear understanding of the stress distribution to enable comparison with the damage mechanism. We can see that the highest stress value acts on the thinnest diameter of the specimen, where crack initiation starts, and it is a stop criterion for the tests. If we look at the cross-section, we can see the stress distribution calculated by an FEM model as well. So the stress, the highest stress is here acting on the surface of the cross-section, and this lead us to the assumption that, like on laser shock peening after multi-axial fatigue, dynamic recrystallization processes could take place on the surface of the specimen. When we look inside the microstructure, we can see that the grain tend to deform in the 1-0-1-0 orientation. The 1-0-1-0 orientation is represented by 25.99%. All other directions are comparatively poorly represented. If we go further and increase the torsional angle, we can see a tendency of the grain structure here again in 1-0-1-0 direction. Also, this could be read in the literature as well, that the alpha grains of titanium 6-4 tend to deform in 1-0-1-0 direction. So the literature states this result. If you look on the kernel average misorientation map, we can see the high angle and low angle boundaries. Here the yellow lines are the low angle boundaries are represented by 53%. The liked green areas are misorientations under 5%. This means that here we can assume a high dislocation density. When we look at the CAM mapping of the sample with higher torsional angle, we can see that the low angle boundary, that the amount of low angle boundary decrease, and that the amount of high angle boundary increase up to 4%. And when we go further and look at TEM investigations, we can clearly see here a high density of dislocation lines contributed to formation of dislocation tangles and walls. This rearrange themselves into subgrain boundaries, and it seems that high strain, which is accumulated during compressive cycling torsion, allows strain-induced subgrain boundary formation. Okay. And this leads us to the summary and conclusion that that with compression cyclic torsion, the sample undergo shear, deform under shear, but undergo compressive strain. That leads us to the conclusion that the cracks are that the crack propagation starts at the surface of the specimen and evolve into the middle in the middle of the sample. And here we can make the conclusion that with accumulation of strain, this leads to increasing the dislocation, and thus the dislocation gradient, the increasing of dislocation gradient. Finally, I want to say that yeah, with higher torsional angle, it becomes clear that the amount of high angle grain boundaries increase, and that as we assumed, like in laser shock peening, after multi-axial fatigue, some nearly dynamic recrystallization processes takes place on the surface of the specimen. So I want to thank you for your attention, and sorry for yeah, the delay.